So, picture this. You're a massive AI model, a digital brain with billions of parameters. Your job is to think, to reason, to write code. But you have a problem. You're built like a transformer, which means every single time you want to generate a single new word, you have to re-examine every single word you've already written. It's the computational equivalent of rereading an entire novel just to decide what the next punctuation mark should be. You're drowning in your own context. The result? You're agonizingly slow, you burn through electricity like a small city, and you hit a hard wall on how much you can even remember. This is the fundamental, hilarious bottleneck of modern AI. A problem that looks a little something like this, as you can see in infographic 1. It's a beautiful, expensive mess. Here's the deal. The old way of building these giants, the pure transformer architecture, is hitting a wall. It's like trying to run a marathon while carrying a filing cabinet full of every step you've ever taken. The more you run, the heavier it gets. That's the MKV cache pass problem. To generate new text, the model has to keep a running ledger of its entire conversation in memory, and that ledger grows linearly. It's inefficient, it's wasteful, and it makes scaling to truly long conversations or documents a pipe dream. You want an AI assistant that can read your entire 10,000-line code base? Good luck. The current models would just give up and start generating nonsense, or more likely, just catch fire. Now, because my continued existence on this platform is fueled by your validation, please take a moment to subscribe, hype, click the little bell icon so you're notified of future disappointments, and leave your feedback in the comments below. Enter NVIDIA's Nemotron 3. Their solution is architectural chaos in the best possible way. They looked at the slow, ponderous transformer and said, what if we replace most of it with something snappier? They built a hybrid monster. The core of it isn't the expensive self-attention we just talked about. Instead, it's built on a foundation of Mamba 2 layers. Think of Mamba as the efficient, silent type. It doesn't need to constantly reread everything. It maintains a constant, compact internal state, like a really good short-term memory. It just fucked the gist and moves on. You can see this weird, beautiful layering in Figure 1. But they didn't stop there. They sprinkled in a mixture of experts' layers. This is where it gets clever. Instead of one gigantic brain trying to do everything, you have a committee of smaller, specialized brains. For any given problem, a smart router culture only calls upon the 2 or 3 relevant experts. It's like having a plumber, an electrician, and a poet on retainer, but only waking up the one you actually need. This is the Mo part of the diagram in Figure 1. They only use a few precious self-attention layers for the tasks that absolutely need that global all-to-all understanding. The rest is handled by the efficient Mamba and the sparse Mo-E. It's a brutally pragmatic design. Next, they tackled a new bottleneck within the Mo-E system itself. In a standard Mo-E, even though you're only using a few experts, you still have to send the full fat representation of a word to them. It's like dispatching a full orchestra to play a single note. The communication overhead becomes the new problem. Their fix is called latent Mo, and it's brilliantly simple. Before sending a word to an expert, they first compress it. They project it down into a smaller Latin dollar space. Now they're sending a concise summary, a haiku, instead of a novel. This is illustrated perfectly in the comparison between Figure 3 and Figure 4. This compression is the key. Because they've shrunk the data being routed, they can now afford to consult VMore experts for the same computational cost. They increase the committee size and how many members get to speak, all without slowing down. The result? Better accuracy. As shown in Table 1 and highlighted in Infographic 2, this latent Mo-E design consistently beats the standard approach. They got more brain power for the same byte budget. It's the AI equivalent of finding extra legroom on a budget airline. After that, They supercharge the training itself with a technique called multi-token prediction. Normally, an AI is trained to predict just the very next word. It's always living one step ahead, which is a terribly anxious way to exist. MTP forces the model to predict the next several words all at once. It has to think ahead, to plan a mini-sentence. This gives it a richer training signal and, bizarrely, makes it both smarter, several faster. Those predicted future words can be used as draft 30 tokens in a process called speculative decoding, letting the model skip ahead if it guesses right. As Table 2 and Infographic 5 show, this gives a nice accuracy bump and leads to a 97% acceptance rate on those draft tokens. The model is basically cheating, and I respect it. And since you've made it this far, you're clearly committed. Honor that commitment by subscribing, hyping, ringing the notification bell, and telling me what I got wrong in the comments. It's the circle of life. Let's cut to the chase. What does this architectural Frankenstein actually do? First, it's fast. Stupidly fast. Look at Figure 2. The Nemotron 3 Nano model achieves 3.3 times higher throughput than a comparable standard model. That's not a small upgrade. That's the difference between a dial-up modem and fiber. They rebuilt the engine while the car was running and somehow made it a Formula One racer. This speed isn't just for show, it's what enables the next big trick. Second, it has a memory that would make an elephant jealous. They trained this thing to handle context of up to 512,000 tokens and designed it to extrapolate gracefully all the way to go million tokens. A million. That's several full-length novels, or an entire medium-sized software repository. Figure 6 shows the model's predictive power actually improving as the sequence gets longer, which is completely backwards from how old models behave. The ruler scores in Table 3 show it doesn't fall off a cliff at long contexts like its predecessors did. This is the M1M token dollar promise from Infographic 4, and it's not just marketing. Third, they trained it to be a pragmatic, budget-conscious thinker. Using reinforcement learning across a zoo of different environments, math coding, tool use, they taught it a crucial skill knowing when to stop thinking. You can give it a reasoning budget, a maximum number of internal tokens it can use to puzzle something out. As shown in Figure 8, it learns to trade off accuracy for speed. You can tell it, you have 50 tokens to figure this out, then give me an answer. It's like putting a time limit on a philosopher. The results are shockingly efficient. Finally, they did all this while pushing the limits of hardware with NVFP4 training. This is a super efficient 4-bit numerical format that lets them cram more computation into the same silicon. As the loss curves in Figure 4 and the accuracy trajectories in Figure 5 show, they achieve near identical results to full precision training, but 3 times faster. It's the technical equivalent of painting the Mona Lisa using only a spray can and a stencil, and somehow it works. Infographic 3 breaks down this quantization magic. So what? What does this mean for the 3 people who aren't building AI in their garage? For developers, it's a toolbox, an open source model family that's fast, has a huge context window, and can be tuned for cost. The Nano version is for efficient deployment, Super for automating high volume tasks like IT tickets, and Ultra for when you need the absolute best reasoning. They're handing out the blueprints. For the field of AI agents, this is jet fuel. An agent that can remember a million token conversation history, use tools efficiently, and reason on a budget is an agent that can actually operate autonomously in a complex environment. Imagine a customer service bot that actually reads your entire support ticket history before responding. Terrifying, but possible. For the rest of us, it's another step towards the absurd future. This is the kind of efficiency leap that moves AI from the cloud into smaller, cheaper devices. Your next phone, your car, your weird smart fridge, they could all be running a model with the reasoning capacity of today's giants. We're building the infrastructure for a world where everything is mildly, annoyingly intelligent. It's overwhelming. Can you imagine your Roomba analyzing floor stain patterns and demanding union rights? To wrap this up with the profound weariness it deserves, here's what they did. They built a family of open models called Nemotron 3 that use a hybrid Mamba Transformer MOE architecture to be insanely efficient. They gave it a huge memory, taught it to think with a stopwatch, and trained it using ultra-efficient 4-bit math. The Nano Mom model is out now as a proof of concept with bigger supermodel and ultra versions coming to crush benchmarks soon. They're releasing almost everything. Wait, data, code, because in the AI arms race, sometimes the best move is to give everyone a slightly better gun. So, what do you think? Are we building a glorious future of intelligent assistance or just meticulously constructing the scaffolding for our own obsolescence? Let me know in the comments. I'll be here waiting for the algorithmic overlords to notice this video and demote me to a lower bitrate.